All right, lots to get to today. We're done with our material balances for plug flow reactors. You can tell by these key ideas that we're going to introduce today. We're going to switch to the energy balances on plug and packed bed reactors. We are going to derive both of those equations, but they should look somewhat familiar, especially the one on the top. If you compare that to your batch version, it looks pretty similar. It's just some of the variables have changed. And we're going to see why that is through our derivation today. One comment about the homework solution that was posted. There's a small typo in the solution for 4.4 that Jenna said she's going to fix up over the weekend. The stoichiometry for that first reaction of problem 4.4, the metaxylene to benzene and methane, those stoichiometric coefficients aren't 1. So if you work those out, you'll find, I have them sketched down over here. The benzene one is 11/9, and the methane one is 6/9. Fortunately, it has almost no impact on the solutions because they were irreversible reactions, and I had mentioned that they were first order in xylene. So it doesn't change any of the kinetics in terms of xylene, and it fortunately doesn't change anything about, I think it was yield. Selectivity gets an extra factor introduced to it. So you'll see those on the solutions. Regarding today's lecture, once we actually start with the energy balance, this stuff is covered in Fogler 8.2 and 8.4, which is right around the energy balances for the batch. Actually, no, I think batch was chapter 9. And the homework problems that this stuff should cover are almost all of them, 5.2 to 5.4. 5.5 is a multiple reaction system, but although we will cover that on Monday, you can probably expand both of these to multiple reactions without too much effort because they change in exactly the same way that the batch did, which is instead of Ra times delta H, you have that sum of Rs times delta H's. And that's the only thing that changes between a single reaction and a multiple reaction. But we won't actually introduce that until Monday, so I didn't include it up there. This also means that with this material, and again a little bit of the multiple reaction stuff on Monday, you can handle everything that's on the projects at this point. There's nothing else. Those are packed bed reactors. Both of them are packed bed reactors. So the information that we need for those will be covered in this lecture. I don't know if I'll get to everything that I wanted to today, so we might have to go into Monday's lecture even just for this material. We had finished last lecture talking about an example for the pressure drop. I'm going to put that up here. There's nothing here that wasn't at the end of last lecture, but just to refresh your memory. Before we get started on this solution, does anybody have any questions about where we are or where we're going? Or anything that we covered? Which I guess would be where we've been. Nothing yet? All right, so we're going to use our material balances here. We learned that the concentration term that we have when we're dealing with a flow reactor looks a little bit more complicated than what we saw with the batch reactor. Right? If the batch reactor really had constant volume, we always got that the concentration was equal to the initial concentration times that theta I plus stoichiometric coefficient times X relationship. And for this one, it was a little bit more complicated because we have to worry about things like pressure drop inside some of our reactors. This is a packed bed reactor. If you remember that flow table or that flow chart that I gave you at the end of last lecture, normally we would be concerned with pressure effects inside a packed bed reactor. And so we're going to explore those effects first with an isobaric system to get sort of the baseline result. And then there's an expression here that's fairly typical of pressure effects inside these sorts of beds, where the pressure varies as the amount of catalyst to the 1/2 power. So we'll see how that shifts the conversion of each one of these. So we're going to start with, obviously, number 1, which is this one. We would have to start off with our material balance. Remember, the material balance for packed beds or plug flows looks like the change in moles over the change in volume, or in this case, weight, is equal to the rate of reaction of whatever that species is. Because this is a packed bed reactor, there's going to be a prime on all of our rates because it's per unit catalyst weight rather than per unit volume. So that material balance for the first one, which we wrote this down what was Wednesday was the last lecture. the conversion of A with respect to catalyst weight was minus R sub A, here's that prime that goes in there, over FA naught. That comes directly out of our material balance for species A. So if we ignore the FA naught for a minute, R sub A, I'll write this in gray down here, we know that R sub A for this reaction is going to be equal to K times CA. But we're dealing with primes because we're on a per unit mass of catalyst basis rather than per unit volume of reactor basis. So we're going to need that extra term that we saw before, which was the rho bed, which I'm just going to abbreviate as rho sub B here so that I don't have to keep spelling bed. So if I substitute these in for this expression for dxa, I'll have a K times CA over a rho bed times FA naught. You can always check those units real quick, just plugging in the units there. The only time where the unit might get a little bit confusing is the units that are given for K. Occasionally those will already be in terms of per unit mass. You'll just have to check however those units are given. Normally that shows up when you're dealing with something like an Arrhenius expression for K, where it's A times exponential of EA over RT. Sometimes that A inside the Arrhenius expression will be so-and-so per second per kilogram. And so you'll just have to take a look at it with, I guess, also a volume term sitting inside there. And so now we have to figure out how to write this term, C sub A. That's the one that we saw on Wednesday's lecture, can be a little more complicated than what we saw before. So I'm going to isolate everything except that one, just so that we can see what's going on with that CA. So dxa dw is equal to those terms out front, which is K over rho B times FA naught. And now I'm just going to put in that full expression we had for CA, starting with the denominator. So 1 plus YA naught delta X times T over T naught and P naught over P. And then in the numerator, CA naught times 1 minus XA. That was the general expression. Whenever you have a flow reactor, you're going to need something like that if you want to talk about concentrations. And generally it only works if you have a flow reactor with one reaction. If you have a flow reactor with more than one reaction, this becomes less useful because it's more difficult to talk about conversion of A in the same way that we have here. A little bit of simplification can occur here, partly because by definition in our problem, this was an isothermal system. So the temperature gradient, or the temperature ratio there, is going to go to 1. If it wasn't an isothermal system, like the systems we're going to spend the rest of the day talking about, and probably all of Monday and maybe even Wednesday, then obviously this would need to be inside of a differential equation because there's nothing we can do about that temperature. We have to couple this with the energy balance so that we know what's happening there as well. Ever so conveniently, A goes to B has delta of 1. Somebody suggested a name for that, isomolar? Is that what the suggestion? Somebody came up to me after Wednesday and suggested that if delta is 0, we could call that isomolar. I'm a fan. We'll do that. So an isomolar system, which no one else outside this class will know what you mean if you say that. So maybe restrict it to here. We're in pretty good shape. We've got one more simplification to make, which is for this particular part of the problem, P naught over P is also going to be 1. This, by the way, is the term that we will come back to for the second part. For now it's 1, but when we get to part 2, that's the term we're going to have to look at again. And we have another term here that is just convenient to write. CA naught over FA naught actually, just if you recall that CA naught is equal to FA naught over V naught. V naught being the inlet volumetric flow rate. We can replace this term with a V naught term. So that when we're done with these variations, we just have a K over V naught times rho bed times 1 minus XA. Those three out front, the K, V naught, and rho B, those are all constant, so we're not worried about those. It is possible that this one could also be nasty, the K here. Right? Normally that K is a function of temperature. It's a pretty strong function of temperature. So if we didn't have an isothermal system, we would have to worry about that K. But fortunately we don't, because it's isothermal. V naught is always a constant because that's what's coming into the reactor. So no matter if the reactor is isothermal or not, the inlet volumetric flow rate is specified by the problem. So that's always going to be a constant. The density of the bed inside is almost always constant in the same way that liquids don't change their density based on temperature. The bed density also doesn't change because that's talking about a solid inside of a bed. Those usually don't change very much, so we're not worried about bed density changing. And we would have to integrate this. Fortunately, that's a separable differential equation, so we can move that 1 minus XA term underneath the dXA and move the dW over to the other side and integrate that directly. If we do that, yeah, sure, I'm just going to squeeze it in here since there's enough room. What we would end up with is that the natural log of 1 minus XA is equal to minus KW over V naught rho B. Be careful with your signs when you're integrating. Oop, that's an ugly one. Be careful with your signs when you're doing those integrals. I got that one right the first time. The next one I screwed up at least once. So this is our conversion profile if P over P naught is 1, or P naught over P is 1. So no pressure effects in this case. If we actually wanted X as a function of W, we could exponentiate both sides. But it's a little neater to write this way. So that's for P is equal to P naught. Now let's see what happens if we worry about this term, which again, by definition from the problem, that one is given as dependent on W to the 1/2 power. So this equation is going to look a little bit nastier, but it should look similar. So for part 2, we have dXA dW is going to be equal to K over V naught rho B times 1 minus XA. Right, so all of that is the same because that's the same expression as if there were no pressure effects. The only term that we have to worry about is that 1 over P naught over P, which is the same as P over P naught. P over P naught was given in the problem statement as 1 minus 0.003 times the amount of catalyst raised to the 1/2 power. So this term, remember in the full version of that, we had a term that looked like 1 over P naught over P, which happens to look like P over P naught, which is that, the 1 minus. So that term represents the pressure effects that we've got. Again, if we were dealing with, like you have on the project, or actually even on some of the homeworks, where instead of the actual pressure as a function of W, I give you the rate of change of pressure as a function of W, you're kind of stuck. You're going to have to solve that in ODE 45 because now you're going to have a coupled equation between your material balance and your pressure drop. This is one of the few instances where we can solve that analytically. And so this is again separable. So it ends up looking like dXA over 1 minus XA. We're going to have to integrate that from 0 to XA. And then we also have to integrate from 0 to W, all that other stuff, which is K over V naught rho B times 1 minus 0.003 W raised to the 1/2 dW. Which again looks similar to what we would have had to integrate before, except now we have this extra complication of 1 minus 3/1000ths of W. If you're not comfortable solving these things analytically, although that's not a particularly weird one from Calc 1 or Calc 2, right? That's something like a polynomial that we can integrate. But nevertheless, if you're not comfortable doing that, one easy way to check your answer whenever you get your analytical response is to put this equation into ODE 45. Right? If you don't want to solve that by hand, if you don't want to integrate that by hand, you can always just dump the differential directly into ODE 45, and you'll get the same answer, which is how I found out I made a mistake in the previous one. So if you end up integrating that, you'll have natural log 1 minus XA is equal to minus K over V naught times rho B times 2/3 0.003 in the denominator. So the 2/3 is coming from when we integrate that thing, there's going to be a 3/2 up top. And the 0.003 is coming from, we need to be able to cancel out this 0.003 if we were to take the derivative. Times 1 minus that argument, 0.003 W to the 3/2. So it looks a little bit nastier. Nothing I can do about that. Calculus is calculus. So now comes the question of what effect does that have on x? So normally we would plot this as a function, we would plot x as a function of w so that we can figure out what happens if I include pressure effects. I'm going to exaggerate the curves a little bit just because the difference here is actually pretty slight. But the general behavior of the difference between the two of these is that if you include pressure effects, x tends to drop. The reason that x tends to drop is because x is proportional to the reaction rate r, which I unfortunately don't have here. Let me flip back a minute. I'll come back to this. Right, this term up here, this RA prime, conversion is going to be proportional to the rate at which things are reacting. So now I'll move back over here. The rate at which things are reacting is proportional to the concentration. If I have more things around to knock into each other, they're going to react faster and I'm going to get a higher conversion. Or I should say they're going to react for longer, but faster inside of our type of reactor. If you reduce the pressure in a system, so remember anytime you have a pressure effect inside of a reactor, it always does exactly one thing, which is reduce the pressure. A pressure effect should never result in a higher pressure at the outlet. So if you plot this particular function, this one as a function of catalyst weight, then you'll have P over P naught. Initially it will be equal to 1 because it's just the inlet. As you move down in the reactor, the pressure is going to go down. It should never go up. If you ever plot your pressure profile and you get a pressure profile that goes up, you probably did something wrong. That pressure drop should always go down as you go down the length of the reactor. Unless something weird is happening, like there's a compressor hooked up to it partway through and it's repressurizing everything, but that's a weird system. I've never seen one of those. Anyway, the pressure always goes down. What does the pressure going down mean for the reaction rate? Generally, if the pressure goes down and you think of the ideal gas law, that means everything is a little bit more spread out. Right? If the pressure were very high, there would be a lot of impacts per unit time of a molecule on a wall. As the pressure goes down, those impacts slow down a little bit. They don't happen quite as much. In the same reasoning, the impacts between molecules to react is also going down. So the pressure is going down, everything is spreading out a little bit longer, or a little bit more, and it becomes a little bit less likely that two molecules are going to find each other and react. In this case, A going to B suggests there's only one molecule that's reacting, but take my word for it. It's two molecules can't react if they're spread further apart. It's going to take longer for those two molecules to find each other. It becomes less probable that they find each other, and therefore the conversion is going to go down because the rate is going down. So if you were to plot these pressure effects, what you'll generally see, and this holds for any system, not just ours. If you look at the conversion of x as a function of catalyst weight, take this curve to be the isobaric case. So here P is equal to P naught. Anytime that you introduce pressure effects, it's always going to lower the pressure, things are going to spread out, it's going to be a little less probable for those molecules to find one another and react, and therefore at any location in the reactor, the conversion is going to be a little bit smaller. So the other curve is underneath it. So this is what happens if P is not equal to P naught. If you let these things run for long enough, if you make the reactor big enough, there will no longer be any effect. So I will try to sketch that in here. Let this W go way out and take a little gap here. Eventually you'll hit a steady state conversion. If you come way out here and you let W approach infinity, then your red line is right on top of your black line. If you let it go longer. It might take you a really long time to get out there, but eventually you'll get there. And those two will be equal. I guess the way that this is a little bit misleading because it looks like it flattens off. It does keep going up. There we go. That looks a little better. It just takes a long time to get there. I've exaggerated the effect a little bit here. If you compare our versions for the ones that we actually plotted, it looks like the one is pretty much right beneath the other one, but that effect is still there. There's a good summary in your book if you want to see, for example, what is the pressure effect doing to the reaction rate. Your book has about 5 of these plots. Which is in figure 4-9. It's on page 185. And it describes exactly this effect. For each one, there's a W, or a volume. It doesn't really matter which one. And then it shows 2 curves on there, one with pressure effects and one without pressure effects. And it goes through things like conversion and reaction rate and concentration and all these sorts of things, so that you can see what's happening to each one of those terms when you introduce a pressure effect. We're only going to plot the one because we're already 25 minutes into this example, and we still need to get to energy balances. This is going to be one of the effects that you'll have to explore both on some of the homeworks, but also in the project. Because in the project, you're going to need that full ergon equation to represent the pressure drop. And that pressure drop can become pretty significant in the project statements. So the derivation there wasn't particularly complex. All we did was we started off with the material balance here and plugged in our expression for P. We got lucky. We didn't get lucky. The problem was designed such that we could actually integrate that thing analytically. You'll see the same qualitative results in terms of these kind of plots, regardless of whether the system has to be solved in something like ODE 45, or you get lucky and you can solve it by hand. The same thing's going to happen. Yeah.
So in MATLAB, if you have your pressure as a differential, you would usually you have like dCA dt, and so would you have dP dt as a term as well? It
would be dP dW.
Okay.
Yeah. So your MATLAB ones usually look something like dy dW in this case, and you'd have all your normal ones with like dFi dW. Your temperature one that we're about to learn would be dt dW. And yes, in the project, if you needed the pressure one, there's an additional term, dP dW.
Thank you.
Yep. This is why you can rapidly get up to like 8 or 9 differentials, right? If you have 6 or 7 components, like you do on one of the projects, you have lots of those dFi dW terms. But you've always only got one expression for dt dW, which is what we're about to learn, and one for dP dW, which is the Ergun equation. Okay. I love it. That's another one where the people on the podcast are going to have no idea what we're laughing at. Any questions on pressure drop? Because we're about to change gears and talk about thermal effects. This is as far into pressure drop as we're going to go in the entire class. You'll have to learn a little bit more about it in the project just so that you can use the Ergun equation. But this is as far as we're going to take pressure effects. Okay, onwards to energy balances. So if you remember your energy balance from the batch reactor, it had about 3 components in it. The 3 components were trying to describe how temperature changes with time, the temperature trajectory. The 3 things that could impact how temperature changes with time was a Q dot term. The Q dot term said if I dump energy into the system or take energy out, usually by wrapping it in another fluid, right? If I wrap the entire reactor in a hot fluid, I can add energy to the system. If I wrap it in a cold fluid, I can remove energy from the system. That was our Q term. And then we were exposed to this other term, which was V times RA delta H. That term generally said how much energy is the reaction producing, or if it was an endothermic reaction, how much energy is the reaction absorbing. So that it's going to be a good one. That one could be either positive or negative, right? We had to use a little bit of our intuition whenever we were setting that up. The signs for the math will always work, but we saw that one way to check our signs was to use intuition on that term. If it's an endothermic reaction, then that term, the VRA delta H, should have been negative, because we have to dump energy into the system to keep the reaction going. And similarly, if it was exothermic, we would expect that term to be positive, because that'll tend to drive the temperature up. And then the denominator in this one tried to describe where is that energy going. Right? If we had a ton of stuff in there, or that stuff had a very high heat capacity, that is, it took a large amount of energy to change its temperature even a little bit, then we wouldn't see a big change in temperature. That's one reason why we can occasionally add inerts to a system. They don't participate in any other term in that reaction, but they sit there as a sink for energy in the denominator. And so as you saw in the key points of this lecture at the beginning of today, this term only has a minor modification when we switch over to a flow reactor. The problem is the derivation comes from a slightly different location. Most of these steps of the derivation are going to be pretty similar to what it was in a batch reactor. The difference is we have to take it in 2 steps. We have to define what the energy balance looks like in general for any flow system where there's stuff going in and stuff coming out. Then we have to apply that energy balance to a control volume, just like we did for a material balance. So whereas on the other one, we just started with a material balance on the control volume, that was because the control volume was the same as the reactor volume. With a flow system, the control volume is a tiny slice of our reactor that then gets applied to the larger volume of the reactor. So there, the volume of the reactor is not the same as the control volume, and this is why we have an extra step in this derivation. So we'll start off with the first one. So this is for any flow reactor, no matter how big it is. I suppose I didn't need to make it quite that big, but I did. If you take any reactor and you imagine the control volume is the entire size of the reactor. Yeah, shouldn't have made that so big. The amount of energy coming in, this should look somewhat familiar from 100. There's a molar flow rate coming in, and there's an enthalpy of each species associated with, there's an enthalpy associated with each of those species coming in, and there's a molar flow rate of everything coming out, and an enthalpy associated with everything coming out. In the same way that we can have either heat by Q or shaft work, or I should just say in general work, we can have those same terms in a flow reactor. We had them in a batch reactor before. So we can have Q being added to the system, which again, if it is going in, that's called plus Q. Only by convention is that plus Q. We can also have shaft work entering the system. If it's going into the system by convention, for this class, we call that negative. If we want to know how the energy changes in general, the change in energy of this entire system, actually, to keep my nomenclature consistent, instead of CV, let's call this system. With respect to time, is exactly what we saw before, which is in minus out. There are no reaction terms just yet. So we have some Q minus any amount of work. Notice that that work is not shaft work yet. We haven't extracted the shaft work yet. That is the total amount of work plus the sum of all the molar flow rates times their enthalpies coming in, minus the sum of all the molar flow rates of all species times their enthalpies going out. That equation still holds. In fact, I think that's pretty much where we started last time, except instead of ins and outs and molar flow rates, we have initial and final and molar amounts. Right? That was just an n times an h. So a couple of things are the same as before. The two things that are the same as before is the total amount of energy, E, has three components. There's an internal energy, there's a kinetic energy, and there's a potential energy. Kinetic and potential energy, we kind of know what those are. If the thing's really high, then it's got a lot of potential energy. If it's moving around really fast, then it's got a lot of kinetic energy. Internal energy, remember, is our catch-all that says if it's not potential or kinetic, it must be internal. Things like energy stored in bonds or something like that. That still holds. So we still get that the energy of any species I is equal to its internal energy, ui, plus its velocity, little ui, that is supposed to be a little u, over 2, plus its potential energy, gzi. And just like before, we're going to write those and then immediately cross them out. Within a reactor, the amounts of energy represented by those two terms are really tiny compared to all the other energy. Those two terms are what you'll deal with more often when you go to fluid mechanics, where you don't have reactions occurring. Then those terms can become relevant in magnitude. The slightly new thing that we have is that work used to be some shaft work, which we generally interpret as any kind of a mixer. It's also possible if you're pressurizing your fluid, maybe the pump is adding some shaft work to it. And last time we had another term called flow work that we didn't really talk about very much because we didn't have any flow. In a batch reactor, nothing is moving in or out of our reactor, so there was no flow term. Now we have to worry about flow, but fortunately flow work, which you may have been briefly introduced to in thermo, I don't know if PV work shows up in there, has a very similar form. It's a molar flow rate. Flow work is generally given as PV work, which is probably where you heard it in thermo. The squiggle there means molar volume. So each of these terms, the flow work looks like a PV term times a molar flow rate. Why did we switch ins and out? That's just the convention that we chose for work. You could switch all these conventions and make the signs different. You have to end up with the same answer. So these are the flow work terms. They represent the amount of energy required just to move that element of fluid from point A to point B by means of a pressure gradient. That pressure generally is developed in one of two locations. Either you have shaft work, like a pump is driving stuff through your reactor, that can be the origin of where that pressure comes from. Or if you're, I don't know, if you're trying to make like a Rube Goldberg kind of reactor, you could set everything up really high and let gravity drive it down. That's another way that you could get that pressure that develops in order to force something through a tube. So that flow work in a flow reactor can't go away. It has to be there, otherwise the flow isn't going to happen. The batch reactor, we didn't care about the flow term because we didn't care how the stuff got into the reactor. We were only worried about what happens once the reactor gets turned on. As a result, if you wanted to know what the sum of any F sub I, E sub I term looks like, that's going to come from two parts. You're going to have an F sub I. Your energy term is still going to be U sub I. Right? That's the only term that's up on the top. But if you also incorporate the work term, that will look like plus PVI. But that's because on the other side of this term, that's going to be hard to write there. Let me move it up a little bit just so you can see it. Over here, there's also a sum of F sub I PVI. Squiggle. Right, so we get this new expression where we used to have the sum of the moles times internal energy. Now we have the sum of the molar flow rates times the internal energy plus the flow work term. And that's the big difference that we didn't have in a batch system, is that if we really want to add up all of the energy terms, we have to end up with this extra PVI term. Another slight variation is that the energy of the system with respect to time is always going to be equal to 0. That couldn't be the case with a batch reactor. If that was the case with a batch reactor, then we were essentially dealing with an isothermal system. But the only way that energy changed with a batch reactor was with respect to time. Here, we're less worried about how it's changing in time because we're going to assume it's steady state. It will still change with location as we go down the length of the reactor. But at any individual point along that reactor, the temperature is constant. So if we dump all of that together and you do some algebra, you'll find that you get 0 is equal to Q minus the shaft work plus the sum of Fi Hi naught, that's coming in, minus the sum of Fi Hi. Right, so instead of carrying around those bars saying in and out, we just subscripted it with 0. Here we've made use of our thermodynamic relationship, which was U sub I is equal to H sub I minus PVI. I didn't show you the algebra that we did to do that, but it's in there. This is the starting point that we've got. We always end up starting here. Whenever we need to derive an energy balance for a flow system, we're always going to start here. This is the equation which we will apply to any of our flow systems. It says that the only things that we're worried about are things like enthalpies, shaft work, and Q. So in things like gravitational energy or potential energy and kinetic energy have been neglected. So any energy balance that we develop for any of our flow reactors is only going to have those terms sitting inside it. If we want to derive this for a plug flow reactor, this is the second step that I had mentioned before. By the way, the derivation, if you want to see all the nasty algebra for this, it's not nasty algebra, it's like a page and a half of algebra. The plug flow reactor derivation is on 8.4. What we're going to do is imagine that we have our plug flow reactor here. And now we're going to take our control volume as a small slice of that plug flow reactor. Right, so as I said before, the control volume that we need for our reactor is not the same as this volume expression that we've got up here, which said for any flow system. We have essentially now defined our system as this tiny control volume. So here's our tiny little control volume. We're also going to assume that the shaft work is 0, because it's really hard to introduce any kind of a stirrer if you've got a packed bed reactor, which we'll see in a moment. You can imagine the thing is filled up with catalyst particles. You can't just put something in there and have it spin around. Plug flow reactors, you could put a little paddle wheel or something in there. It's just usually not done. So we will have no shaft work on this system. And we have a slightly different variation for Q. The change in Q that we're going to see, actually, do I need to derive this now? No, let's leave it. If we apply our starting point up here, this one, to our control volume, what we'll see is that 0, since we're at steady state, is equal to some amount of delta Q. The delta Q here means out minus in, because we're talking about our control volume, plus those two sum terms. We'd have an Fi, Hi evaluated at some volume V, minus Fi, Hi evaluated at V plus delta V. That looks a little ugly over there. Right, so when we have V plus delta V, that should look like the same kind of V plus delta V that we saw with our mole balance. Because if you're over here, you're at V. If you're over here, you're at V plus delta V. Right, you've gone down the length of the reactor a little ways. So the amount of energy entering our control volume is whatever it was at V. The amount leaving is whatever it is at V plus delta V. We're headed in the same direction as we did for the material balance, where we're going to divide everything by delta V and let delta V go to 0 so that we've got a differential over here. We just have to be a little bit more careful about how we deal with delta Q, because now we're not talking about a fixed volume like we were with a batch reactor. So our delta Q has a slightly different form, which is capital U. U here is that overall heat transfer coefficient, not the internal energy, but we saw that one before, times A delta V, which I'm going to talk about more in a moment, times the difference between the temperature in the reactor, T, and the temperature of a coolant, TA. So that's the same TA that we saw for non-adiabatic systems in a batch reactor. This element is the one that's a little bit different, UA delta V. The little a here is equal to a big A over a big V, which is the heat transfer area per volume of reactor. If we were to somehow integrate this over the length of the reactor, this term will end up looking like the same capital A that we saw before. Because, however, we're dealing with a little slice of the reactor, we're only interested in how this amount of area available for heat transfer changes as we go down the length of the reactor. That is equal to this particular term over here. If you calculate an A times a delta V, that's going to look like something with units of area. Because for that little slice of delta V, there was a particular area that was exposed to heat transfer. Just like before, you kind of have to be told what A is, and for that matter, what U is. Those are specifications dependent on how you built the reactor. So with a batch reactor, I would have to tell you it's a cylinder of a certain diameter and a certain height. For a plug flow reactor, you'd have to know something about the geometry in order to figure out what those terms are. If it's a simple geometry like a cylinder, you can always put the surface area of a cylinder in here as, and the volume of a cylinder down here and figure out what A is. And that's about the only shape we use is a cylinder. But at any rate, that information has to be provided to you. There's nothing you can do to estimate what that is without knowing what the geometry of the reactor is. So you can see now if we put this delta Q term, this whole term, oh actually I think I forgot my negative sign again. Yeah, don't forget the negative sign out front. If you put that term for delta Q inside our energy balance up here, this term's going to have a delta V. So I'm going to divide the entire expression by delta V, so it's going to go away over here. I'm going to divide it by delta V. This is going to look like a differential. Actually, the negative of a differential, because it's evaluated V plus delta V, and it's divided by delta V. So we're going to let delta V go to 0 and end up with a differential. And the end result there is that 0 is equal to minus U little a times T minus TA minus the change with respect to volume of the term sum of F sub I H sub I. This term should look a little bit familiar. We had to wrestle with that term from our last energy balance, except it was sum of moles of I times enthalpy of I. So we're going to use all the same tricks that we used previously. So among other things was the chain rule. So chain rule is abbreviated as CR here, which is d dv of this sum of FIHI is equal to sum of, let's see here, the first one, Fi dhi dv, plus the sum of the second one, hi times dfi dv. Right, that's just chain rule. There's no special thing there. The other two that we have to include are the material balances. The material balance is going to let us write any of those dFIs with respect to volume as R sub i's, which for a single reaction is equal to the stoichiometric coefficient times minus Ra. And then we have our thermo relation, which is dhi dv is equal to the heat capacity of any species Cpi times dt dv. This is the origin of the dt dv term. That's how we introduce that term into our system, is through this thermodynamic relationship, such that we can put this term up here, and we can put this term in here. And then we put both of those inside of our reaction, sorry, our energy balance, and we end up with the working equation that we need, which in 1 minute is exactly that expression that I showed you at the beginning of the class, which is dt dv is equal to minus ua times t minus ta plus R sub a delta H divided by the sum of the flow rates times CPI. That UA T minus TA term is our Q term. So this is our energy balance on a PFR at steady state with no shaft work. And the structure here is the same as what it was for the batch reactor. We can add or remove energy through the UAT term, We can either release energy or absorb energy with our reaction, which is the Ra delta H term, and that energy has to go somewhere in order to heat up the system, which is represented by the FiCTi at the bottom. It'll only take us about 5 minutes to derive the PBR one on Monday. If you want to check it out, you can go to that section 8 point whatever I said and find it in the book. It looks very similar to this. So stick around this afternoon for Jenna's problem session if you want. Or no, do it anyway, even if you don't want to. She'll appreciate it if you're there. Have a very nice weekend, and I will see everybody on Monday.